This circuit adds two numbers. 13 plus 42 gives 55, and there is no processor anywhere inside it. There is no software either. What you are looking at is nothing but switches wired together in the right order. Because everything in it is this. A transistor, it is a switch with no moving parts at all. Put a voltage on the gate and current flows. Take the voltage away and it stops, on or off. One switch can light a lamp. That is not interesting. What is interesting is that a few billion of them run an operating system. So here is the promise. By the end of this video, this pile of switches will run an instruction. No steps skipped. We build it in order. Start with two switches in a row, wired between a power supply and a lamp. For the lamp to light, current has to get past both of them. If either one is open, nothing happens. Only one combination out of the four turns it on. That pattern has a name. It is called and it is our first gate. Now take the same two switches and put them side by side instead of in a row. Now either path is enough. Close one or the other or both and the lamp lights. That is OR. Series is and parallel is OR. Nothing else is going on here. The whole of logic is switches arranged two ways. There is one more gate, and it is the odd one out. Wire the switch so that closing it drags the output down to ground. Now the output is high when the switch is open and low when it is closed. It is always the opposite of the input. That is not. Three gates, and, or, and not. That is the entire parts list for a computer. Every calculation your machine performs, all of it, is these three shapes repeated. So let us wire them into something that counts. Adding one bit to one bit. There are only 4 cases, so let us just do all 4 of them. Zero and 0 is 0. 0 and 1 is 1, 1 and 0 is 1, and 1 plus 1 is 2. which in binary is written 1, 0, 2 digits. 3 of the cases fit in 1 bit, the fourth does not. So 1 output wire is not enough. We need 2, a sum and a carry. Look at the sum digit first. 0, 1, 1, 0. It is 1 when the inputs differ and 0 when they match. One or the other, but not both. That is exclusive OR. XOR is not a fourth kind of thing, by the way. It is 5 of the gates we already have, wired together. So XOR gives the sum. Now the carry. It is 1 only when both inputs are 1, and that is exactly AND. Two gates fed from the same 2 inputs. This is a half adder, and it is the first circuit here that does arithmetic. So why is it only half an adder? Because it adds 2 bits, and real numbers are added in columns. Every column after the first has 3 inputs, A, B, and the carry coming in from the column before it. Our half adder has nowhere to put that. Here is the trick. Build the 3-input adder out of 2 of the 2-input ones we already have. The first half adds A and B. The second adds that result to the incoming carry. Either half can produce a carry, but never both at once. So one OR gate collects them into the final carry out. 5 gates in total, 2 XORs, 2 ANDs, and 1 OR. Here it is, wired for real. 3 switches going in, 2 lamps coming out. Watch it walk through every combination. One plus 1 plus 1 is 3, which in binary is 1, 1. Both lamps light, and that is correct. Eight possible inputs, 8 correct answers, and not a single special case anywhere in the circuit. It simply cannot be wrong. From here on we stop drawing the 5 gates and draw 1 box instead. Full adder. This is genuinely how chips get designed. Build a thing once, verify it, then stop thinking about its insides forever. So let us line 8 of these boxes up in a row and add a whole byte. 8 full adders, 1 for each bit. The carry out of each one feeds the carry in of the next. That is the whole design. There is nothing else to it. Around 40 gates, and it will add any 2 bytes you give it. So let us feed in 13 and 42, the 2 numbers from the very first shot of this video. Watch the carry travel. The rightmost column settles first because it has nothing to wait for. Bit 3 is where it gets interesting. 1 plus 1 is 2, so it sends a carry to the left. That carry changes the answer in the next column, which could not be worked out until it arrived. And there it is, 55. This design tells you 2 things. The first is that it is slow. Bit 7 cannot settle until bit 0 has. The delays add up, gate by gate, which is why real chips use carry look-ahead instead. The second thing is the ceiling. (255 plus 1 gives 0. The last carry has nowhere to go. That is overflow. Now a problem. Everything we have built so far forgets instantly. Take the inputs away, and the output vanishes with them. A calculator that cannot hold on to a number is not a computer. We need a circuit that stays where you put it. So do something that sounds like cheating. Point the output back at the input. 2 gates, each one feeding the other. Press SET and the output goes high. Now let go of it. It stays high. Nothing is driving it anymore. Each gate is holding the other one in place. The loop itself is the memory. Press reset and it flips back to 0 and stays there. That is a latch. 1 bit remembered. Put 8 latches side by side, and you can hold a whole byte. That is a register. It is the fastest memory a computer has, and the only memory the arithmetic circuits can reach directly. A processor core has a few dozen, not thousands. Now the machine has both halves, something that computes and something that remembers what it computed. But there is a fatal problem. Nothing tells it when. Left alone, it would race around that loop as fast as electricity allows. Here is the part nobody mentions. Electricity is fast, but it is not instant. Every gate takes a moment to switch, and the high bits depend on the low ones, so they finish last. For a few nanoseconds, the output is simply wrong, a half-computed number. The fix is not to go faster. The fix is to agree on a moment. That is all a clock is. Between ticks, the wires can do whatever they like, because nobody is looking at them. On the tick, every register copies its input at the same instant, so the clock is not what makes a computer fast, it is what stops it being wrong. When a chip says 3 gigahertz, that is 3 billion of these moments every second. Which leaves about a third of a nanosecond between one tick and the next. In that time, light travels 10 centimeters. Every tick, the slowest path in the entire chip has to finish. That is why chips are small. At these speeds, distance is time. We have arithmetic, memory, and timing. One piece is missing, telling the thing what to do. And an instruction turns out to be just a number, like everything else in this machine. Chop that number into fields, and each field means something. The first is the opcode. It picks the operation. The rest pick registers. Decoding it is not magic either. It is one and gate per instruction. Each gate watches the opcode bits and fires only for its own pattern. Exactly one output line is ever high. That line switches on the circuit that does the work. Opcode 0001 lights the add line. So here is one complete instruction, running one tick at a time. Tick 1, fetch, read the instruction sitting at the program counter. Tick 2, decode, the and gates light the add line. Tick 3, execute, the adder we built adds 13 and 42 together. Tick 4, right back. The register we built stores the answer, and the counter moves on. Register 1 now holds 55. The instruction ran. Look at the chain. Switch, gate, adder, register, clock, decoder, processor. Nothing was skipped and nothing was hand-waved. Every box was built out of the one before it, and all of it came from a switch that is either on or off. A real chip adds two things on top of this. The first is that it never does one thing at a time. While one instruction executes, the next is already being decoded and another is being fetched. 4 in flight at once. That is a pipeline. The second thing is that there are rather more switches. Our full adder is about 20 transistors. The Intel 4004 from 1971 had 2,300. The chip in your phone has roughly 20 billion. Nobody understands a chip by reading all of it. They understand it the way we just did, one block at a time. The promise at the start was that this pile of switches would run an instruction. It did, and every wire that put 55 in that register was one we built. There is no further layer underneath. If you want to feel it, open a free logic simulator, drop in an XOR and an AND, and wire both to the same two inputs. That is a working half adder. Next time, the processor is fast and it spends most of its life waiting. Caches and the memory wall.